In 1961, a meteorologist named Edward Lorenz sat before a primitive computer at MIT running weather simulations. In a moment of scientific serendipity that would forever change our understanding of complex systems, Lorenz made a seemingly inconsequential decision. He rounded a variable from 0.506127 to 0.506. When he returned to his simulation later, he discovered that this tiny alteration, a difference of less than 1 part in 1,000, had transformed his weather prediction entirely. This discovery gave birth to chaos theory and its most famous concept, the butterfly effect. As Lorenz would later ask in his landmark 1972 paper, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" With this poetic question, he captured the essence of deterministic chaos, the notion that in certain systems, microscopic changes can cascade into macroscopic consequences, making long-term prediction fundamentally impossible. Chaos theory revealed something profound about our weather and climate systems. Despite being governed by deterministic physics, precise equations that describe the motion of air masses, the exchange of heat, the formation of clouds, these systems exhibit extreme sensitivity to initial conditions. The atmosphere operates like an enormous amplifier, where small perturbations grow exponentially rather than linearly. Lorenz demonstrated this with his famous Lorenz attractor, a three-dimensional plot resembling a butterfly's wings that visualized how a system could be simultaneously bound within certain parameters, yet never repeat itself exactly. The trajectory of the system would forever dance around specific regions, what mathematicians call strange attractors, without ever settling into a predictable pattern. This discovery demolished the Laplacian dream, the 19th century notion that with enough information and computational power, we could predict everything in the universe with perfect accuracy. Lorenz proved that even if we could measure atmospheric conditions with perfect precision, which we cannot, tiny measurement errors would still render long-range weather forecasts impossible beyond about 2 weeks. Yet climate science persists. How can we make claims about climate trends decades into the future when we cannot predict weather beyond 2 weeks? The answer lies in the difference between weather and climate, the difference between predicting the path of a single leaf in a turbulent river versus predicting the river's overall flow. Climate represents the statistical properties of weather over time. While individual weather events remain unpredictable, the statistical behavior of the system, its climate, can be more reliably forecast. This is why climate scientists speak in probabilities and trends rather than certainties, why they project ranges of temperature increases rather than exact forecasts. Nevertheless, chaos theory reminds us that climate systems contain tipping points and nonlinear responses. Past a certain threshold, feedback loops can drive rapid, irreversible changes, like the potential collapse of ice sheets or shifts in ocean circulation patterns. The climate system isn't just complicated, it's complex, with emerging properties greater than the sum of its parts. Modern climate modeling has embraced Lorenz's insights rather than being defeated by them. Today's climate models don't attempt to make point predictions about weather decades from now. Instead, they run numerous simulations with slightly varied initial conditions, an approach called ensemble forecasting. The statistical distributions of these outcomes provide more reliable projections than any single forecast could. These ensemble approaches acknowledge the inherent uncertainty while still extracting valuable information. If 95% of model runs show warming exceeding 2 degrees Celsius under a certain emission scenario, that represents actionable information, despite the impossibility of predicting exactly which days will be hottest or which storms will be strongest. Climate scientists have also incorporated chaos theory into risk assessment frameworks. Rather than treating uncertainty as a reason for inaction, they apply risk management principles. The greater the potential harm, the more prudent preventative action becomes even amid uncertainty. This approach mirrors how we handle other chaotic risks, from financial markets to public health emergencies. The story of chaos theory and climate science contains a fascinating paradox. Our understanding of deterministic chaos has made us simultaneously more humble about prediction, yet more confident in the need for action. We now know both the limits of our predictive capabilities and the reasons why those limits exist. This scientific humility doesn't translate to ignorance or helplessness. Rather, it's produced more sophisticated approaches to understanding and responding to climate change. Modern climate science acknowledges that while we cannot predict with certainty which coastal cities will flood in which decade, we can confidently state that sea levels will rise, and we can quantify the range of possibilities under different emission scenarios. One particularly valuable insight from chaos theory is the concept of strange attractors, the regions toward which chaotic systems tend to evolve. Our climate system has existed within a relatively stable strange attractor for roughly 12,000 years, the period known as the Holocene, during which human civilization developed. The concern today is that anthropogenic emissions might push Earth's climate toward a different attractor state. Historical climate records reveal that Earth's climate has made dramatic jumps between different regimes in the past. Ice core samples from Greenland show that temperatures sometimes shifted by several degrees Celsius within decades, the blink of an eye in geological timescales. These jumps represent transitions between different climate attractors, and chaos theory suggests such transitions can occur rapidly once certain thresholds are crossed. Perhaps the most important lesson chaos theory offers climate policy is that uncertainty isn't a justification for inaction, but rather a compelling reason for precaution. In a chaotic system, the impossibility of perfect prediction doesn't negate the reality of risk. As Lorenz himself observed, chaos, when the present determines the future, but the approximate present does not approximately determine the future. This insight is profound for climate ethics. Our approximate knowledge of climate risks is sufficient to demand responsible action, even if we cannot determine exactly how climate change will unfold in each region. The butterfly effect reminds us that small changes today, whether in carbon emissions or climate policies, may trigger cascading effects throughout the complex system of Earth's climate. This understanding of chaos doesn't paralyze decision-making. It simply places it within a framework of risk management rather than certainty. Edward Lorenz's accidental discovery unleashed a scientific revolution that transformed our understanding of complex systems. Chaos theory revealed both the fundamental limits of prediction and provided new mathematical tools for understanding unpredictability itself. In climate science, chaos theory has matured from an initial challenge to predictability into a sophisticated framework for understanding climate risk. We've learned that uncertainty has structure, that unpredictability follows patterns, and that there is, paradoxically, order within chaos. As we face unprecedented climate challenges, Lorenz's legacy reminds us that while the specific trajectory of our climate future remains unpredictable, the boundaries of possible outcomes are becoming increasingly clear. The butterfly has already flapped its wings. Now we must prepare for the storms that may come and work diligently to minimize their intensity through decisive climate action.